First off, I'll be talking about the porosity and the available volume fraction and the partition coefficient. Starting off with the specific surface and porosity. So to the right on the slide, you will see 4 different images, and these are examples of porous structures. The black being the solid phase, while the white is the fluid phase. So pores can be empty or filled with fluids, and porosity may vary both spatially and temporally. So the formulas to note are the specific surface, which is S is equal to the total interface area over total volume, and the porosity, which is the E looking symbol, is the void volume over the total volume. And S is over a length while E is dimensionless. That's why S has the units of 1 over m, and E does not have units. But both depend on the structure of the pores. So why is this important? The specific surface is a measure of the absorption capacity of various industrial absorbents, and it plays an important role in determining the effectiveness of catalysts and filters. And also the porosity is a factor in separation in catalyst processes, which is really important for future jobs within industry or anything like. So our first example is when you're given a problem and it's determining the specific surface and porosity of a porous medium with a uniformly distributed cylindrical pores. So it will usually give you a diameter, a length, can give you the NA or the N, and then you'll have your cross-sectional area. So you would start this problem by first solving N is equal to NA times A. You would use the formula of the total interface area, which in this case is pi dl times N, and then you find the total void volume, which in this case is d to the 4th power over 4 times pi L and then times N. And then using what you found with those different formulas for this particular case and shape, you'll be able to find the specific surface, which in this case is N times pi dl over AL, which is actually just equal to pi d and A. And then the porosity, which is the in this case is pi times d squared over 4, then times NA. Moving on to the available volume fraction and the partition coefficient. So there are 3 types of pores, just for some background on this. This can be a passing, isolated, or non-passing pore. And in the lower right-hand corner of this slide, you'll be able to see the different depictions of those 3 different cases. And also, there can be a sum of porosity with these 3 different cases being added up in general. Also, we have the available volume fraction, and this is expressed by the KAV is equal to the available volume over the total volume. Within that, there is also the torosity, which is the finding the distance between points in connected pores, and this is equal to T equals L min over L squared, and this is the shortest distance between the 2 locations. Also, T is always greater than or equal to unity. Furthermore, for the 3 different scenarios where KAV, also known as available volume fraction, is less than the porosity, this is when there is steric exclusion, void space is smaller than the solute, and the solute cannot reach accessible void space. Also, with that, we can find the partition coefficient of the solutes, and this is equal to the available volume over the void volume, also known as KAV, over the E symbol, which is porosity. Now I will be going over example 2, and this is an example problem on determining the partition coefficient and available volume fraction of a spherical solute in a porous medium, using the same picture from example 1, just solving for different things. So first of all, we are going to state the total volume, which is L times the cross-sectional area, but we're just going to call that C. Then we will solve for the available volume, which is pi times d over 2 minus b over 2 squared times L. and then we're going to equal that to A. Once again, this is for cylindrical pores. Any of these equations could be different with a different shape. And then the void volume is pi times d over 2 squared times L, and we're going to equal that to B to make things a little bit easier to manipulate. So we know that the available volume fraction, KAV, is equal to the available volume over the total volume, and using the letters that we've used so far to make things simpler, that will just be B over C. And then we know that the partition coefficient, that is the available volume over the void volume, which we are going to call B over A to make things a little easier. That's also equal to KAV times 1 over E being the porosity, which in the end is just equal to the partition coefficient times the porosity. So also, while making things easier, we're going to show that lambda is equal to B over D. This is the ratio of the radius of the solute to that of the pore. And we'll be able to relate this and use this to further simplify this problem. And that will allow us to determine that the available volume fraction, KAV, ends up being equal to 1 minus lambda squared times pi times d over d squared over 4, and then times the NA. That is our solution for this problem.
All right, so the next concept that we're going to be talking about is flow in porous media. And so this includes things like Darcy's law and then also the Brinkman equation. So the first thing we're going to be talking about is Darcy's law. And so Darcy was a scientist who, when studying the flow of water through sand, he discovered that the flow rate is proportional to the pressure gradient. And so in order to describe this, he proposed a continuum approach, which describes flow moving through porous media. And this requires that there's a representative elementary volume, which can be shown here in the figure on the right, that's considered to be a material point. And so this continuum approach assumes that the medium is a uniform material with 3 length scales. And so the first length scale is delta, which is the average size of the pores, and then the other length scale is the distance uppercase L over which the macroscopic changes of the physical quantities must be considered, such as fluid velocity and pressure. And then there's also L naught, which is the length scale of the representative elementary volume. And so each one of these scales is separated by an order of magnitude. And so by using this continuum approach, Darcy was able to create his law, which is that V is equal to negative H del P, where V is fluid velocity, and then H is the hydraulic conductivity, which is assumed to be constant in homogeneous and isotropic porous mediums. And then del P is the pressure gradient. H is also related to the permeability K through mu, which is the dynamic viscosity. So H times mu is equal to K. It's also important to consider that Darcy's law is invalid for non-Newtonian fluids, Newtonian liquids at high velocities, and gases at very low or very high velocities. Darcy's law also assumes that viscous resistance at fluid and solid interfaces is greater than the viscous dissipation within the fluid. And that means that Darcy's law is only really applicable for small permeabilities. Although it's only applicable for these situations, it is widely used in the analysis of interstitial volume flow. It's also important to consider the continuity equation for flow moving through porous medium, because usually the continuity equation, in order to satisfy the conservation of mass, is del dot V equals 0. But for porous mediums, there are sometimes sources and sinks, and so this is accounted for in the modified continuity equation, where del dot V is equal to phi B minus phi L, where phi B is the flux of the source and phi L is the flux of the sink. And so by plugging the Darcy law into the modified continuity equation, you can get negative del dot H del P is equal to phi B minus phi L. And then a special case of this is del squared P is equal to 0, which is when H is considered constant and there's no sources or sinks. Another important consideration for Darcy's law is that if the pores are not cylindrical, there have been expressions for H that have been derived by scientists such as Kaczynski based on the Navier-Stokes equation. So for example, for non-cylindrical pores, H is equal to C times epsilon cubed over mu S squared. And then the values for C, which is the shape factor, are shown here on the right for different types of shapes of the pores. Now moving on, As I mentioned, the Darcy law was only for a specific case, and so this is remedied by the Brinkman equation, which serves as a connection between Darcy's law, which works for low permeability, and then Stokes' law, which is for high permeability. And so this can then be applied to more cases of flow in porous medium. And so this is proven here. So at low permeability, the mu over K times V term is much greater. So that reduces the Brinkman to the Darcy law, whereas for a high permeability, you can get the Stokes equation from the Brinkman equation. So it shows its utility in describing flow of porous mediums. And so now we're going to do an example of fluid flow in porous media. And so this question is asking us to determine the hydraulic conductivity H and permeability K of the porous structure shown below. And so here we're going to assume that the fluid is Newtonian and that the pores are cylindrical and parallel to one another. The diameter of the pores is D, their length is L, and the total number of pores N is equal to the cross-sectional area A times lowercase n, which is the number of cylinders per cross-sectional area. So the first step that we're going to use in solving this problem is to use Darcy's law to find an expression containing H. And so we can recall that V is equal to negative H del P. And so we're going to assume that the fluid is only moving in the X direction. And so that reduces to V is equal to negative H dP over dx. The second step then, and our kind of general strategy for solving this question, is going to be comparing the expression for V using Darcy's law and compare that to the average velocity moving through the porous medium. And so to find the average velocity, first we have to find just the normal velocity moving through a cylinder by using the continuity and Navier-Stokes equations to develop an expression for V moving through the porous mediums and through each pore. And so I'm not going to show the actual derivation of this, but you can get V through moving through a cylinder is equal to negative dP over dx r squared over 4 mu times 1 minus r over r squared. Step 3 then is to find the average velocity and then compare that to the velocity as I just described. And so recall that the average velocity is equal to the total flow rate over the total cross-sectional area. And so we want to find the total flow rate. So we're going to find Q for the flow through N cylinders. And so Q is normally the integral of the velocity over the entire area. And we're just going to multiply that by N. And so we can expand this by doing the integral from 0 to 2 pi and 0 to R as the total area of that pore. And then we can continue expanding this by substituting the expression that we have for velocity into that integral, and then evaluating that integral to get that Q is equal to negative R to the 4 over 8 mu times dP over dx, all multiplied by N. And then we can substitute D over 2 in for R. Then now we want to recall that uppercase N, the total number of pores, is equal to lowercase n times A. And so then we can continue expanding the expression for Q as negative pi d to the 4 NA over 128 mu times dP over dx. And so finally, now we're able to find the average velocity. And so that just cancels out the A term from our Q expression. Now that we have this, we're able to compare it with the Darcy expression and see that the value of H is equal to pi d to the 4n over 128 mu. The next step then is to find K, and this is pretty easy since we know that relationship between H, mu, and K. And so then we're able to find that K is equal to pi d to the 4n over 128. Now we're going to move on and talk about flow past immersed objects. And so this involves things like drag, finding the drag coefficient and drag force, as well as the different geometries and how that affects flow over those different objects. And so the first thing is drag, and drag will result from the relative motion of a fluid moving over an object. And it's really just a net force on a submerged object due to the pressures and stresses acting on that object. And so there's two main types of drag, the first one being skin or wall drag. And this is caused by the tangential shear stress on the surface parallel to the direction of flow and occurs within the boundary layer. The second type of drag then is the form drag, and this is also known as pressure drag just because it's caused by pressure gradients as fluid flows over nonlinear objects. And so this causes additional frictional losses and can be reduced by streamlining the object to reduce that wake at the back of the object. And so this is an example of those two different types of drags on fluid flowing over a sphere. And so as you can see here, the skin drag is present within the boundary layer, and that's caused by shear stress. And then the form drag is at the end because the sphere is nonlinear. Now going into the actual mathematical representations of things, you can define the drag coefficient as the ratio of the total drag force per unit area to the velocity head. And so this is shown here in SI and English units, where the velocity head is equal to rho V naught squared over 2, where V naught is the fluid velocity, and then A in the drag force per unit area can change based on the geometry. From this expression, then you can find the total drag force, which is equal to CD times 1/2 V naught squared rho times A. And then another important quantity that we want to consider is Reynolds number, which helps describe the type of flow regime that a fluid has. And so this is equal to length times velocity times density divided by dynamic viscosity. So in this case, it's d v naught rho over mu. And that's very important in describing fluid behavior. Now moving on, we're going to be talking about the different geometries. Now that we have this tool belt of the drag coefficient and drag force, we want to describe how these change based on the geometry of an object. And so there are different relations between the Reynolds number and the drag coefficient for each type of geometry, and these correlations have been determined experimentally and then graphed for specific object types such as spheres, cylinders, and disks. And so there are some common factors or commonalities between these different geometries. These are described here. And so one of those is streamlines, which describe the fluid velocity or fluid path around the body. And these can be seen here on the figure on the right as these arrows pointing to the right. There's also stagnation points, and that's the origin of the boundary layer. Where the fluid first meets the object and where the velocity is 0. And then there's a separation point, which is the area where the boundary layer separates. And that's what causes a wake, which is characterized by these large eddies and can cause form drag, as mentioned before. And so, as I mentioned, these relationships between the drag coefficient and Reynolds number have been plotted for different types of geometries, and this can be seen here. And so in the lower Reynolds number region, that's for more laminar flow, whereas Reynolds numbers in the upper regions 10 to the 4 and upwards include turbulent flow. There are some special cases, however, based on the geometry of an object. And so one case is that for laminar flow around a sphere for Reynolds numbers less than 1, it's actually been found that the experimental drag force is actually the exact same as that predicted by Stokes' equation. So then you get the drag force is equal to 3 pi mu d times v naught. And then in this scenario, you can also solve for the drag coefficient as 24 over Reynolds number, which is a really cool relationship. So now we're going to do an example problem of fluid flowing over different geometry just to see how the type of geometry can change fluid behavior. And so in this example, we're asked to find the drag coefficient and force on a sphere that's being subject to air at 37.8 degrees Celsius and 101.3 kilopascals. That's flowing past the sphere, which has a diameter of 42 millimeters, and the air has a velocity of 23 meters per second. And so the general strategy that we're going to be using to solve this problem is to first find Reynolds number and then use that figure that I showed before to find an associated drag coefficient for a sphere and then calculate the drag force using this drag coefficient. And so the first step is to find Reynolds number, and we can recall that Reynolds number is equal to d times v naught times rho over mu. And we already have the values of d and v naught, so now we just need mu and rho for air at 37.8 degrees Celsius. And so by using Appendix A3 from the textbook, we're able to get that the viscosity is equal to 1.9 times 10 to the negative 5, and the density is equal to 1.137 kilograms per meters cubed. And so we're able to compute Reynolds number for these conditions as 5.781 times 10 to the 4. And so now moving on to step 2, we're able to use this Reynolds number and use this figure to determine the drag coefficient associated with that for a sphere. And so by using this, we're able to find that the drag coefficient is around 0.5. And so now moving on, since we have the drag coefficient, we can calculate the drag force using that equation we saw earlier, where the area is equal to 1/4 pi d squared, which is the area that the fluid is intersecting cross-sectionally for that sphere. And so we're able to calculate that the drag force is equal to 0.1958 newtons.
Alright, so let's move on and talk a little about packed and fluidized beds. So packed beds are basically a collection of these uniformly distributed particles in which a fluid can flow through. As you can see in the bed on the left there, these particles should be quite small compared to the whole bed. Otherwise, there's going to be some undesirable interactions with the walls. And for the sake of discussion, we're going to assume that the void volume is small enough such that the fluid passing through can't channel, like it has to take a narrow winding path through the particles. As you can probably already tell, packed beds have some of the same parameters as porous media. This void fraction, for example, is essentially porosity. Packed beds also have their own version of a specific surface, which we start finding by taking the ratio of a particle's surface area to the particle's volume. We can simplify this significantly for the case of a spherical particle and rearrange these terms to kind of generalize a calculation for particle diameter. This is called effective or equivalent diameter, and we'll use it a lot later. Finally, we can find the total surface area ratio by multiplying the particle's specific surface by what essentially represents the total volume of particles, this 1 minus epsilon term here. At the bottom here, you can see how the dimensions play out to give us this A. I'm not going to spend too much time on shape factors, but they do come up later when we talk about fluidization. In layman's terms, shape factors describe how particle shapes differ from that of a perfect sphere, values closer to 1 being most spherical. You can see a table down here for some common geometries and their shape factor values. The series of equations on the right are all useful in solving for the shape factors, provided you know information about your particle's surface area. And again, this dp is just the effective diameter we calculated last slide. Okay, so if we want to describe flow through these beds, a good place to start would be coming up with an equivalent expression for Reynolds number. While our fluid density and dynamic viscosity may be the exact same, we need to modify our velocity and characteristic length. The velocity is fairly straightforward. We're going to use what's called the superficial velocity, v prime, which physically is just the velocity of fluid entering or exiting the bed, provided there are no sources or sinks. This regular v is the average interstitial velocity, which represents the actual fluid velocity as it travels inside. For our characteristic length, or diameter, we're going to use 4 times the hydraulic radius. You can see that by following the dimension conversion on the far right, we end up with an expression we can describe in terms of our bed, which equivalently is stated here. And lastly, by making the appropriate substitutions we just accounted for, we end up with a new formula that describes the Reynolds number in packed beds. Okay, so as you can imagine, laminar and turbulent flow are going to behave differently and need individual equations to describe their flow. The only new parameter in these equations is delta L, which simply represents the length of the bed. The laminar case is called the Blaise-Cassini equation, which is actually just a rearrangement of the Hagen-Poiseuille equation, substituting in the appropriate hydraulic radius and solving for delta P. Experimental data is used to adjust for the fact that the actual delta L is a bit larger than the bed's delta L, as the fluid cannot make a straight line from entrance to exit. The turbulent case is called the Burke-Plummer equation and is a rearrangement of a friction factor equation. This equation is chosen because as flow becomes turbulent, it has been shown experimentally that the friction factor becomes constant, which is why it isn't present in the equation. Again, the appropriate hydraulic radius is subbed in and the equation is rearranged to have delta P on the left there. What's neat about this is Ergun, who is actually a chemical engineer I believe, found that by combining these two equations, we can have a generalized expression for bed flow that works for any Reynolds number. You can see that if viscosity, for example, is significantly dominant, only the left side of the equation will be relevant, which is what we'd expect for laminar flow. Alright, moving on to fluidization. So fluidization occurs in an upright bed when the force exerted by the pressure difference exceeds the particle's gravitational force, and this of course causes them to move. Another thing to note is that the pressure difference no longer increases past fluidization. This is because the movement of particles causes these large fluid pockets to form, almost as if the particles are boiling. So typically we're concerned with minimum fluidization, which as you saw on the last slide is the point at which fluidization just occurs. The values of the bed length, void fraction, and superficial velocity are all different at this point, and if we calculate some of them experimentally, we can solve for the others using math. The first equation is essentially a statement of the conservation of mass, as the total volume of the particles themselves and their density should remain the same from rest to fluidization. So if we measure the bed length while it's fluidized, solving for the fluidized void fraction is a matter of algebra. However, as you can see, determining superficial velocity at this point is much more involved. I put it in this table to hopefully help you follow. We start with equation 1,1, which is a force balance with the force from pressure and the gravitational force on the particles. Again, when these are equal, we are at our minimum fluidization point. This is easily rearranged to equation 1,2, which is a useful form for later. Equation 2,1, as you might recall, is our old friend the Ergun equation. We can transform this into equation 2,2 by dividing both sides by bed length and replacing dp with its shape factor equivalent. Do note that the dp in equation 2,1 represents the equivalent diameter for the actual particle, while the dp in equation 2,2 represents the diameter of a perfect sphere with an identical volume. Finally, we can equate equations 1,2 and 2,2 to give us a single equation in which we can inevitably solve for superficial velocity. Lastly, when you have an unknown shape factor or void ratio, do keep in mind the two relations on the right. These have been found to be true for most packed bed systems. Alright, let's go ahead and do an example problem of what we just talked about. This problem is from the provided packed beds chapter. I like it because while it is about fluidized beds, you have to have some implicit knowledge on packed beds as well. Alright, so I'm just kind of dubbing over this footage because I was writing pretty slow and want to speed this up. But as you can see in the top right, I have my little bank of parameters. The ones in the top box are explicitly given in the problem, while the ones in that separate box there are actually all tabulated for error at the given conditions. So part A is very simple. All we're after is this minimum fluidization height. We start by using our given total particle mass and particle density to find total particle volume, which looks to be about 0.3 cubic meters. We can then divide this by the bed's given cross-sectional area to find the bed's height at rest. Next, we can recall the implicit mass balance we were discussing on the last slide. You may notice that while we have epsilon for our minimum fluidization, we are missing epsilon at rest. Since we did not account for any void volume in our total particle volume, we can assume, well, not assume, we know, that epsilon 1 must be 0. From there, we can rearrange and solve for our minimum fluidization length, which should be about 1.7 meters. For part B, we're calculating pressure drop at minimum fluidization. We really only need to recall one formula, which is the force balance we said must be true at minimum fluidization. The only parameters needed, which aren't listed at the top there, are G and LMF. Of course, G is just gravity, and we solve for LMF in part A. So now the answer is almost handed to us. There's so little rearranging. The pressure difference should be about 9,800 pascals. Part C requires us to calculate minimum fluidization velocity, which involves that monster equation we created on the last slide. The good news is that all the parameters besides V'(f) are known to us, so once it's all written out, we're just solving a quadratic. I went ahead and just used my calculator for this part. And since this is a quadratic, of course you're going to get two answers. Only one of them is going to be positive, and due to the way the bed is oriented with fluid flowing upwards, this is the only sensible answer. I went ahead and wrote the answer stated in the solution section beneath my answer. You can see that we were quite close. And part D is literally the same scenario, only this time we're told we can't use the given void volume nor the shape factor. This isn't an issue, as we can plug in those approximations I was talking about on the last slide, as indicated. Again, solving this quadratic gives us a result that is a bit farther off than what we got in part C, but still fair.